Okay, one other thing that we have here. So this is our base instantaneous voltage equation. We can always use this one. We do have a couple others depending on our situation that we can use. When we're charging from zero, so if we're starting at 0 volts, if we were to put this through, we could go through and simplify this down. So we're charging from 0. Voltage of the capacitor is equal to voltage final times 1 minus E to the negative T over tau. Yep, to charging charging from a 0 voltage. So basically we're assuming there's nothing on it already. 1 minus E to the negative T over tau. So it simplifies it down a little bit. Yeah, so if we're discharging, so it's set up to charge from 0 up, or we're trying to go from some value down. The formula we can use is this. Is that. So there are a couple of special case scenarios. Just like we had with parallel, we have the main one that we use is the reciprocal method, and then depending on if this case is true or this case is true, we have a couple of different options. So same with this. If you just remember and use this guy, you'll be just fine. These ones just simplify those values down. Those are taking into account you're starting at 0, going to some value. This one is taking into account you're starting at some value, going to 0. So you could derive these from that formula. All right. So the equation that we have that we're going to look at, so we have a DC circuit, we have a capacitor, and we have our resistor. We have 14 volts. Capacitor 1 is 150 microfarads, and resistor 1 is 1.2 kiloohms. Now what we want to do is we're going to look and see what our voltage is across the capacitor at different times, the different taus, figure out all this information. So we're going to kind of chart this guy up. So the first thing we need to know is, what is our tau? What is our time constant? What's our formula for finding tau? Resistance times capacitance. So tau is equal to 1.2 kiloohms multiplied by 150 microfarads seconds. Yeah, tau will be in seconds. 180 milliseconds. So every 180 seconds, we're going to hit a tau. Does not matter at all. We also we refer to this as tau. The other name that's commonly thrown around is the RC time constant. Yep. You can do them. That's just double points. Oh, that's the lab. The lab, the relay lab in next week's lab, don't do. I got to move it over to the next semester. Okay, so we have 180 milliseconds. Let's see. Where is that? Okay. So what we're going to do is we want to chart the information. So we're going to go from tau is equal to 1, 2, 3, 4, and 5. We want to go all the way up to 5 tau, which is fully charged. First thing I want to know is how much time is that going to take? What's the voltage of the capacitor at that time? And what percent of my VT are we at? So tau, 1 tau is 180 milliseconds. So our time, how much time has elapsed? 180 milliseconds after 1 tau. After we've gone 2 tau, 2 time constants, how much time has elapsed since we turned on the circuit? How much? 360. Okay, after 3 tau, after 4 tau, and then after 5 tau, 900 milliseconds. Okay. We take tau, which however many time constants we've gone, with our base tau. We multiply them across. Yeah. So, yep, 2 tau is equal to 2 times RC. 3 tau is 3 times RC. So tau is our base time constant, and we want to go till 5. Now remember, the values we're looking for are this. I'll put these guys in red. I said we had 63.2%, 86.5%, 95%, 98.2%, and 99.3%. We're going to verify that the answers we get match up with those. Okay, so the first thing we're going to do is we're going to go through and solve this equation. We're looking at it as in reference to time. So this is where we're going to come into with the logs. So first thing we want to do is we want to solve for the voltage of our capacitor at 1 tau. So we need to use our instantaneous voltage equation to solve for this value. So the voltage we have, voltage of the capacitor, is V final minus, or plus, V initial minus V final times e to the negative t over tau. Okay? We're not going to use the other formulas. We're just going to practice with this with our large formula first. So we're trying to solve for this value at 1 tau. VC is what we're looking for. What is the final voltage we're trying to get to? What's the final voltage that this capacitor can charge to? 14 volts. Because when this capacitor finally does, what's going to happen when it's fully charged? It's going to open, and what else is in the circuit? Just a resistor, so we're not going to split the voltage anywhere. So when we measure across this, what are we going to measure? All 14 volts. Okay, so we have 14 volts plus, where are we starting out? At 0 minus 14 times E. What's our time? What's our tau? So when we're at 1t, or when we're at 1 tau, what does our exponent go to? 180 over 180. So we end up with a negative 1. So when we're right at the time constants, we know how this is going to end up. We have the time of negative 180 over our tau, which is the 180. So when we plug this into our calculator, what does this give us? Yep. So we're going to work through this order of operations. So we have 14 plus a negative 14 times e to the negative first.
Do you have a CIE, right? There's two e's on it. The one that's like the natural log, this is the green button. It's e to the x. Yeah, that one. Yeah, that one works for me.
That's the one you want. Okay. So how much voltage does that equal? We'll round it out to 3 digits. That's our formula. Where are we starting? So we're starting at 0. That's VC at tau equals 1. Okay? So if we put that value in, we have 8.850. The percentage of our VT, so let's solve for that. So if we go 1 full time constant, we're going to get that value. Yep. We could. Yeah, we're always going to start from 0. Okay? So now, we're going to shift. Now that we've got it at 1 tau, we want to know what's my capacitor charged to when we get 2 tau. So we're going to take this equation becomes negative 2. Because our time, we've gone 2 tau, we've now gone 360 milliseconds. So we have negative 360 milli over 180 milli. So when we're dealing with tau, we can completely eliminate this portion of it because we know how much time, we know the relationship. We're looking for 2. So if we plug this value in, (12.105 volts). When we have 12.105 volts, anybody have a problem with that? Okay, we move to 3 tau. Again, nothing's going to change other than our exponent. So 14 plus a negative 14 times e to the negative 540 milli over 180 milli. That's going to reduce to -3. What voltage do we get to there? 13.303 volts. When we multiply it out, what percentage do we get? 95%. Okay, here's a trick question. We're going to work it backwards. Since we have this pattern, what voltage would we expect just based on this value, our 98.2? How would we find that? Yeah, 14 times 0.982. We could also find this by plugging in that formula with E changing to -4. So the taus are really easy to find if we can remember these percentages. Again, I'm not expecting you guys to memorize them, but to understand that it's not linear. It's an exponential curve. And how many tau does it take to fully get charged? 5 tau. Okay? So the last one, VC at 5 tau. So we have 14 plus a -14 times e to the -5. What voltage is that? Okay, so here's another question. So now that we figured this out, we can see what the value of our capacitor is. How much voltage do we have across the resistor at each of these points? We have the remaining, because it's going to split up. It's a series circuit. That voltage has to split up. So what we see is we don't just see a solid voltage value. We're going to see a ramp. Tomorrow, I will bring in, I'll show you guys this. I'll set up the example that I have built, and we can actually go through and you can see this charge and discharge in real time. That's one of the things you're going to be doing in lab, is you're going to be watching this and you're going to be timing it and making sure to, and you're trying to dial in your calculations as far as you can to get exactly 10 seconds. That's part of the lab for next week. Okay? Now this is all good and great when we have specifically our taus. Okay? These percentages are just there to give us roadmaps, or to give us landmarks, benchmarks. Where should we be at this amount of time? Not always are we going to be dealing with numbers exactly dealing with 1 tau, 2 tau, 3 tau, so on and so forth. Okay? There are minutes.
So what's the cases where we'll have an initial voltage that won't be 0?
Depending if you start out with a cap pre-charged or not. Sometimes you're going to have a situation where it'll never get down to another value, so you can start going from there. There up is the idea. Yeah. Capacitors put into the system, or we have a battery or something that's charging it, and then we're adding another voltage into it. Or a diode. Things like that. Okay. So here is a test, or here's a quiz question. I have this circuit. Okay. One of the things that we need to start understanding is now I'm going to be looking at an output. When I build these circuits, they're not just to build a circuit, they're with something in mind. like we had with the loaded bipolar voltage dividers, we're using them as to power something else. We have to be aware of where this output is being taken off. Because if we take the output here to ground, it's going to give us a different value if we were to take it off the capacitor. So if we were to take it off of this, what would the graph of our voltage look like? Yeah. So we would start up at the full voltage, and it would charge and discharge and look like this, with our output taken across there. If we had these flipped, we would see our curve back coming from our capacitor. So in the test question, what we have is we're given, what was it, 24 or 14? We're given 24 volts. My capacitor is 39 microfarads. And I have 300 kiloohms. So the first thing it wants to know, what is tau? And the second part of information, it says the capacitor 1 has no initial charge. So it's starting out, it's been discharged fully. We want to know what is my voltage at a specific time. So what is tau? And what is my voltage of the capacitor at, let's see, 45.63. Okay, so tau, so this is the two questions. What is my tau, and what's my voltage at this specific time? Okay, so tau, remember, is R times C. So 39 micro times 300 kiloohms. And Max, what did you say it was? Straight? 11.9, okay. Yep, 46.63 seconds. Okay, so how do we set this equation up? We want to know what the voltage of the capacitor is, so which formula are we going to use? The instantaneous voltage. Okay, we want to know how much time or how much voltage it's going to be at this time. So we just plug in every value when we solve for it. Okay? So our phi final, what voltage are we charging to? 24, because there's no other capacitors in here. So we're going to have 24 plus, what's our initial value? 0, minus 24, times e to the negative time is 45.63. Over tau. This is an instance where we're not having a specific 1, 2, 3, 4, or 5 tau. That was given to us. It says we want to know the voltage at this time. Okay, first thing I want to do is double check my answer. Okay, just so I know where I'm supposed to be. So 45.63 divided by 11.7 is what? 3.9. So we know at 4 tau, it's 98.2. So we can take this value and we can double check ourselves as we do this. We know my answer is going to be less than 4 tau, which is 13.748 volts. So we can kind of double check ourselves as we go to make sure we get the right answer. We're not quite at 4 tau of time. We're not going to be quite at this percentage of voltage. Okay? So when we plug this value in, what is So let's see. So VC at 4 tau. I'm just going to put this in just so we have it as a reference. This is just kind of as a reference point. So we know we're just slightly less than our time, so this voltage should be less. What is the voltage of my capacitor? 23? Oh, I took 14 instead of 24. That's what I did. Yeah. Okay, and what did you get? Okay, there we go. I just still had the 14 stuck in my head from previous. So, our answer, does it make sense? Yes, because it should be slightly less than what we are at 4 tau. So it gives us kind of a checks and balance with these percentages. Okay? Any questions with finding that? At this point, it's really straightforward. All we're trying to do is solve the equation for whatever voltage it is. Okay? Same equation, same circuit. I want to know how long is it going to take me to get to 15 volts? How would I start solving this? So what do you got, Zach? Right. Yeah. Okay, let's write it out. So again, we're going to start with our base formula, okay, and go from there. So first thing we're going to start off with is okay, start with the formula. Then let's put in what we know and then solve for it. So the voltage of the capacitor, I said I want to know when it equals 15 volts. We're charging to 24 volts. We're starting at 0 volts. Tau was 7. Okay. Now I'm going to solve for t. This is why we learned logs last week. Okay. So the first thing we're going to do, we're going to subtract 24 from both sides. We get -9. That's now equal to -24 times e to the negative t over 11.7. We divide by -24. Those fall away. One of the key things to know about is what happens if you take the natural log of -1. It pukes. Okay, so there's another check. If this value is not positive, you've done something wrong. It has to be a positive value to be able to take the natural log of it. Taking the natural log of a negative number starts getting into calculus. You can find it, but there it turns into non-real numbers. Okay? So for what we're doing, this should always end up being a positive that we take the natural log of. If it's not, you've done something incorrect. Okay? There's your first check. So we have 9/24 is equal to e to the negative t over 11.7. We need to get to that exponent. So we're going to take the natural log of both sides. So remember, when you take the natural log of both sides, you have the natural log base e of your argument is equal to your exponent. Okay? So in this case, this is our argument, this is our exponent. So we end up with the natural log base e of 9/24 is equal to negative t over tau. It is just natural log. I'm just showing that's why we had to use it, because natural log is base e. Otherwise, we would use log, which is base 10. So there we go. How's that? It's just another function that we have built into our calculator. Okay? So now we take the natural log of this guy. We have our tau. A lot of times when they're doing this equation as well, I will just leave this as tau until we get to the very end, until we need to convert it back. Just because it saves writing on the paper, you're condensing it down, it just makes it easier to move around. Instead of writing 11.7 every single time, we can just write tau because we know what that is. We end up with the 11.7. Multiply both sides by a negative 11.7. So we get times the natural log of 9/24 is equal to time. That's just the formula we have to use. And that's why at the end we want positive time. Because for multiplying by -1 to both sides, yeah. No, it's okay, yeah. If you want to move the just remember, if you want to move a negative over, just multiply it by -1, and that'll move the negative across the equal sign. Okay, so when we plug this into our calculator, what does t equal? 4.6? 11.5 seconds, I will be at 15 volts. Sometimes that's important because what you're looking for is time. Okay, in a television signal, before, like I said, before they went to analog, what it would look like is this. And then, depending on what you're looking at, so this is if we were looking at a color bar. Okay, so if you had, so you got like black, pink, yellow, green, red, whatever, a test signal, as it's scrolling across, what you would see is this. And so what you have to know is you have to know how much time elapses before you get like this negative voltage. That's important. That's how a TV is able to lock onto your signal. I'm not going to steal Shane's thunder, but this is the basic idea of it. Is this signal is the key to the whole television signal. This tells your TV at this time you're going to start displaying information. You're going to start firing your photons across to charge the different colored pixels. Okay? And there is a specific time between here and here. It's a standard. It has to be. So we're waiting for this signal. Once this signal happens, we're going to wait so long, we can set up a capacitor circuit to be our delay. Sometimes it's going to drift, and so TV repairman, you'd come in and you'd fix this time signal. Now, you're not necessarily going to be working on the same equipment, but the idea is the same. When we're calibrating things, when we're doing different measurements, a lot of time we need to know these timing signals. And then we're going to calibrate stuff so that they're firing at certain signal or certain time frames. So a lot of times that involves adjusting a resistor. Because the capacitor is usually fixed, we're not going to put adjustable, it adds more cost to those. The variable resistors are dirt cheap compared to variable capacitors. And again, it comes down to cost. So in this instance, this is why I need to know when this signal hits so much voltage, how long does it take? Because then I can hook up a circuit and I can actually time this thing. So I measure my output. I need to know when it hits 15 volts, and it should be at 11.4 seconds. So let's say we were troubleshooting the circuit. We know it's supposed to take this long. We have it hooked up to our scope to measure time. What could I adjust to get this in there? The resistor. You could dial this sucker in so that at 15 volts, we're reading 11.47 seconds. That is what's considered good for our circuit. We need this signal to hit there after that so much time. Like I said before, when we have programming, when you first power on a board, it's going to power onto a computer chip. It's going to power onto a random state. It's just going to power in with whatever it receives. You want everything downstream to have a delay until you can initialize all your chips. You say this chip start out at 0, this bit start out at a 1. You don't want random things to happen. And so what will happen is you'll go through, as this thing is delaying to turn everything else on in your system, it's going through and saying, I want everything to be shut off. Because once in a while when you turn on the chip, it's going to say, you are on. Well, what you're telling on could be the shredder that somebody's working on. Okay? It could be a robotic arm that's going to swing and whack them in the head. So you want this delay to be like, I want to make sure nothing is being told to move and nothing's moving after a delay. So you could have your master signal be delayed by 11 seconds after turning on your equipment to say, okay, now everybody's authorized to move. We have to get my computers warmed up. We have to get everything going. This is quite a bit of delay, but it could be the matter of saving a life. You sound an alarm saying, hey, crap is turned on. You've got 10 seconds to get out of pinch points. You should have more controls in there than just, here's an alarm, get your butt out or you're going to get squished. If you work in different countries, you might have that problem. Because other countries do not have the same labor laws that we do. They don't care. Somebody gets crushed, there's 15 more ready to take your spot. Okay? That's the nature of the beast sometimes. In America, it's a little bit different because we have it so, we value life. Unfortunately, that's kind of the gist of it, is we value life in America. Okay? But when it comes, like I said with China, they don't necessarily have the same value on life as we do. In different countries, they just throw people at the problem until it's fixed. Quite literally. Yeah. It's horrible, but it's the sad truth. And there may be times where you go to different countries where you have to be conscientious of your own safety. You have to make sure you have things in position so you don't get shocked. Or when you're designing a circuit, you're going to build that in, not necessarily to tell them that it's there, but you're going to build it in because you don't want anything to happen. At least I would hope you guys wouldn't want anything to happen to other people. Yes. Okay, and sometimes it's not the loss of life. Sometimes it can be a loss of chemical. Okay? You can get chemicals that when they mix together improperly, you're going to get a kaboom. Okay? A what? Yeah, noxious gases. That was one of the things we worked with a lot, is we had to make sure that when we turned something on, every single valve was registered in a closed position before you applied power to the valve. You didn't want to actuate it when it was open. Because if you mix, even household chemicals, if you mix bleach and ammonia together, you get mustard gas, okay, which can kill people. So if you're building an industrial robot to clean your house for you, and you have a tank of bleach and a tank of ammonia, and you have one valve that gets, that sends it out, you don't ever want bleach and ammonia in the same thing.
It doesn't feel good. I found out the hard way.
Yeah. Okay. Any questions about solving for these circuits? Okay. Yeah, you should be able to take most of the quizzes. Let me look at them real quick. So you've got DC capacitors in charge. That's your charge is equal to coulombs time, or capacitance times voltage. You've got capacitors in series, capacitors in parallel, capacitors in series parallel, and now you've got capacitors and the time constants and the double points of capacitors and time constants. Double points. There is a triple points, but we haven't talked to there yet. Okay, that's all I've got.